Okay, so myself, Professor Rahul Thawai, I welcome you to the lecture of thermodynamics. Okay, so this course, it is basically in the third semester of the engineering. Okay, and it carries the weightage of 100 marks. Okay, so I will just briefly go through the what will be covering through the session. Okay, so let us see. Okay, I will directly stick to the content because in the limited period of time, okay, we need to cover your compressed syllabus. Okay, so let us start. So this course thermodynamics, it's basically for the 100 marks. Okay, out of 100 marks, okay, 20 marks will be the internal assessment. Okay, and 80 marks will be your university examination. Okay, both internal assessment and end semester exams, they are written. Okay, internal exam, okay, it is for 20 marks, for which we will be conducting UT1 and UT2. Each will be for 20 marks. We'll take the average for those two UTs and it will be counted for the 20 marks. Okay, so that is internal assessment. And we have end semester exam for 80 marks. Okay, so total weightage for the thermodynamics, it's 20 plus 80. Okay, that is 100 marks. Okay, so for the thermodynamics, okay, we don't have any lab session or practical session. Okay, at the same time, we don't have any tutorial or viva examination. Okay, or oral examination. Okay, so simple. Okay, UT plus your final exam. Okay, so this will cover the course of the thermodynamics. Okay, so see what is expected from you. Okay, after the completion of the course, these are known as course outcomes. Okay, so am I audible to everyone? Yes, am I audible?
Yes, sir, you are audible.
Yes, sir.
See, what I expected from you at the end of this course is, see, all of you should be able to apply the law of thermodynamics to various systems. Okay, it might be closed, it might be open. Okay, so for every system you should be in a position to apply the laws of the thermodynamics. We have zeroth law, we have first law, we have second law. Okay, so all these laws you should be able to apply. You should be in a position to apply those laws. So that is what is expected at the end of this course. Okay, secondly, what it is expected is you should be able to compute the heat and work. Okay, so see, there are certain devices which takes heat as an input and produces work as an output. Okay, the reverse case is also possible. There are certain devices which consumes the work as an input, okay, and produces heat as an output, okay, or as a secondary product. Okay, so in both the cases you should be able to compute the heat and work. Okay, you should be able to compute in terms of magnitude of the heat and work. Okay, so that is been expected. In simple, you should be able to calculate, okay, what is the amount of heat transfer, what is the amount of work transfer. Okay, so these all terms are expected. Okay, see, heat can be either received or it can be lost. Okay, similarly, work can be produced, work can be consumed, right? See, simple example, if you take a steel ball and if you put that steel ball, okay, let us consider a steel ball which is at 150 degrees Celsius. Okay, and if you put that steel ball into the water which is at 35 degrees Celsius, what will happen? The steel ball will start losing the heat. Okay, the steel ball is losing the heat and water is receiving the heat, right? So heat might be lost, heat might be received. Okay, same case is with the work. Okay, now see, work can be produced, work can be consumed. If you take the devices like turbine or IC engine, they are basically known as work producing devices. Okay, but if you take the example of like compressor, pump, they are called as, okay, work consuming or power consuming devices. Okay, so in both the case you should be able to compute the heat and work, right? So that is what is expected at the end of the course. Third, okay, you should be able to demonstrate the relationship between various thermodynamic functions. Okay, there are certain thermodynamic functions like Gibbs functions, Helmholtz functions. Okay, now at this stage you won't be able to understand those. Okay, but as the course proceeds, okay, you will be in a position to understand it. I will just brief you some of the functions like Gibbs function, Helmholtz function. Okay. Okay. What is the relationship between these two functions? Okay. So that you should be able to establish. Okay. Third is use of, fourth is use of steam table and molecular diagram. Okay. So you should see there is one table that is called as a steam table. Okay. In steam table, there are basically 5 tables. Okay. Table number 1, table number 2, and table number 3. I repeat, table number 1 and table number 2, let's say table number 1 and table number 2, they are used for either liquid or wet steam or dry steam. Table number 1 and 2, they are used for liquid, wet steam or dry steam. Okay. Now, when we talk about table number 3, 4, and 5, they are used for superheated steam. Okay. Now you might have a question, sir, why we are using table number 1 and 2 only for liquid or wet steam or dry steam? Okay, there are certain reasons. Okay, and those reasons we need to understand first. Okay. So see, wet steam, what do you mean by, what do you understand by wet steam? The steam which contains some moisture or liquid particles, that is called as wet steam. The steam which contains some liquid particle, it is called as wet steam. What is dry steam? Okay, the steam which does not contain any moisture, it is called dry steam. Okay, so table number 1 and table number 2 will be using either for liquid or for wet steam or for dry steam. Okay, now see, table number 3, 4, and 5 will be using for superheated steam. Okay, now question will be, what is superheated steam? Okay, now see, now the atmospheric temperature, okay, now if you talk about the atmospheric pressure, now if you talk about the atmospheric pressure, it's 1.013 bar, right? The atmospheric pressure is 1.013 bar. Now at this pressure, if you start heating the water, okay, now see, now atmospheric temperature is, let's say, 32 degrees Celsius. You start heating the water at atmospheric pressure. Okay, that is basically 1.013 bar. So when you start heating that water, what happens? The temperature of the water will start increasing gradually. Okay. So the temperature of the water, which was at 32 degrees Celsius, it got now increased to 45, 50, 65, 70, 75, 80, 85, likewise. Okay. But once it reaches 100 degrees Celsius, water will begins to boil. Right? Water will begins to boil. So what do you understand from that? At 1 atmospheric pressure, the water will begins to boil at 100 degrees Celsius. At 1 atmospheric pressure, water begins to boil at 100 degrees Celsius. So 100 degrees Celsius, it is nothing but a saturation temperature of the water at 1 atmospheric pressure. Okay, see, water will boil at 100 degrees Celsius, that is correct. Okay, but the reason is that you should maintain the pressure equal to 1 atmospheric. Okay. Now, if you change the pressure, let's say if you want the water to boil at 2 atmospheric pressure, okay, if you change the pressure, then what will happen? The temperature will be changed. Right? The temperature will be changed. So at 2 atmospheric pressure, water will not boil at 100 degrees Celsius. Okay. It will not boil at 100 degrees Celsius. Then at what temperature it will boil? If you want to see that, for that we need to go for steam table. For that we need to go for steam table. Okay, so there is a table. Okay, so which will give you all the properties based on pressure or temperature. Okay, so that is what is expected. See, in detail we will see later on. Okay, so that is what is expected. See, point number 5, compute the efficiencies of heat engine, okay, power. Okay, so we should be able to calculate the efficiencies of the heat engines, okay, like heat engines. So if you talk about the heat engine, okay, what is the engine? Engine is basically the device which converts heat into work. Okay, engine is a device which converts heat into work. Okay, but see, conversion of total amount of heat received into same amount of work, it is not possible. In simple, no device is 100%. Okay, it is impossible to convert all heat receives into work. Okay, it's not possible, right? Okay, because see, there are certain mechanical part, okay, which makes the device, okay, less efficient. Okay, so in that case, okay, we need to calculate the efficiency. So let's say you have supplied 10 kilojoule of heat. Okay, let's say you have supplied 10 kilojoule of heat, and out of 10 kilojoule, okay, only 7 kilojoule gets converted into work. Only 7 kilojoule gets converted into work. Okay, only 7 kilojoule gets converted into work. So just give me a minute. See, I request all of you to keep your mic mute. Okay. Let us come now to the point, right? So see, let's take an example. Okay, let us say for any particular engine, you supplied 100 kilojoule of heat. Okay, you supplied 100 kilojoule of heat, and out of 100 kilojoule of heat supplied, the engine is capable of converting only 70 kilojoule into work. Okay, engine is converting only 70 kilojoule into work. Okay, so 100 was the input and 70 was the output. So 70 by 100, it is nothing but efficiency, right? 70 by 100, it is nothing but efficiency. Okay, so this we are able to we are interested to calculate. Okay, we are interested to compute. Okay, there are certain devices. Okay, the engine is producing a power, right? But there are certain devices which consumes a power, and such devices are called as reverse heat engine. Okay, the example will be a refrigerator. It is consuming a power. That's why it is called as reverse heat engine. Okay, so if it is consuming a power, okay, we are not able to calculate efficiency, right? In such case, we need to go for COP. That is called as coefficient of performance. In simple, you understand. If it's a power producing device, you calculate efficiency. If it's a power consuming device like a refrigerator or heat pump, you calculate COP. That is called as coefficient of performance, right? So so this is a term in which we are interested. Okay, so this is about heat engine, reverse heat engine. See, one more word is written as power cycle, right? So see, power cycle, they can be either, okay, gas power cycle or vapor power cycle. Okay, so vapor power cycle means what? What is vapor power cycle? Okay, by using a vapor as a fluid, we are producing a power. Okay, by using a vapor as a fluid, we are producing a power. That is called as vapor power cycle. Next is gas power cycle. What is gas power cycle? By using a gas, we are producing a power. Okay, so if you want, okay, if you take the example of like auto cycle, diesel cycle, dual cycle, okay, or let's say Britten cycle, all these are the power cycles. Okay, all these are power cycles. Okay, so if you talk about the Rankine cycle, basically Rankine cycle is vapor power cycle. Because in Rankine cycle we are using vapor as a fluid. But when we talk about the Otto cycle, diesel cycle, dual cycle, okay, in this we are using gas as a working fluid. So that's why Otto, diesel, dual, they are called as gas power cycle. Okay, so for all such cycles we should be able to calculate the efficiencies. Okay, that is what is expected. And point number 6, okay, or outcome number 6, it is you should be able to apply the fundamentals of compressible fluid flow to the relevant system. Okay, so see, this is what you can say. This is the advanced part of the thermodynamics. Okay, it's basically called as compressible fluid flow. Okay, so there are certain terms like sonic velocity, Mach number, stagnation pressure, stagnation temperature. Okay, so all those concepts you need to apply, okay, for understanding the compressible fluid. Okay, so is that okay, all of you? What I expect from you from this course? Yes, all of you?
Yes, sir.
Okay, so see, this is, I just give you the brief idea. Okay, what is expected, right? So okay, now see, okay, just a minute. Now all of you see this one. Okay, now see what content will be covering, okay, through this course is our first module. It's a basic concept and first law of thermodynamics. Okay, so first part or first module, it's a basic concept and first law of thermodynamics. Okay, so where we have numerical based on the closed system. Okay, we have numerical based on open system. Okay, so we'll apply the first law of thermodynamics for a closed system as well as for a open system, right? So that, and based on this we'll take the numerical, that is in the chapter number 1, or let's say module number 1. Now when we go to the module number 2, okay, it is the second law of thermodynamics and entropy. Okay, now see, a first law, it carries some limitations. Okay, that is the reason why we need to go for the second law. Okay, so in second module, okay, we'll see the what is the second law of thermodynamics. Okay, and we will extend it for the entropy. Okay, so we'll extend it for the entropy. Okay, see, in second law, okay, there is a concept of efficiency. Okay, in first law, okay, first law doesn't talks about the efficiency. That is a limitation. Okay, that is the reason why we are gone for the second law, which talks about the efficiency. So based on the second law, okay, we will see the numericals based on heat engine. Okay, we will see the numerical based on refrigerator. We'll take the numerical based on heat pump. Okay, we'll take a combined numerical. Okay, so all those things we'll see in a second law. Okay, now see a third module. It's availability and thermodynamic relations. Okay, this is a third module. It's availability and thermodynamic relations. Now see all of you. What is availability? Okay, what is availability? See, availability, it is always calculated with respect to dead state. Okay, so how much energy is available? How much energy is available till you reduce the system to dead state? Okay, how much energy you can extract? How much energy you can extract by reducing a particular system to dead state? What is dead state? It's a condition of equilibrium with the surrounding. Okay, so when you reduce any system to the surrounding conditions, okay, then how much energy you can extract? That is called as availability. Okay, and this we are supposed to calculate, right? And its extension is thermodynamic relation. Okay, so thermodynamic relation. So see all of you, this thermodynamic relation, it is the only part which is the mathematical based, only mathematical based. No numericals are there on the thermodynamic relations. Okay, so in thermodynamic relations, we will see the Maxwell relation, we will see Clausius-Clapeyron equation, we'll see Joule-Thomson coefficient, Mayer relations, all those things we see in a thermodynamic relations. Next is the properties of pure substance. Okay, properties of pure substance. Okay, see, what is pure substance? The substance whose chemical composition remains constant irrespective of phase. Okay, so whenever phase changes, the chemical composition doesn't change. Such substance, it is called as pure substance. Okay, so we are considering H2O, okay, as a pure substance, because if you see the say solid form of the H2O, it is called as ice, right? A liquid form, it's called as water. Okay, and gaseous form, it's called as vapor. Okay, so in all these three phases, okay, the H2O, okay, the chemical composition of the H2O remains constant. Okay, so we'll see the properties of steam. Okay, we'll see what properties of steam. We will see properties of steam. Okay, it is written as pure substance. Okay, and pure substance we assume as a water. Okay, or not of the water, it's a H2O, right? And vapor power cycle, as I told you, vapor power cycle. Okay, so by taking the vapor as a fluid, okay, we need to produce a power. See, vapor will not produce a power directly. Okay, so for that we should have a boiler, we should have turbine, we should have condenser. Okay, so if you are able to arrange all those components, okay, in proper sequential manner, okay, we'll be able to produce a power. Okay, let's say you have water. That water you pump it in a boiler. Water you pump it in a boiler. In boiler you add the heat, so water will be get converted into vapor. Now that vapor you supply on the blades of the turbine, right? So blades of the turbine will start rotating and they will start producing a power. Okay, see, when you allow the steam to flow on the blades of the turbine blades of the turbine will start rotating, right? And see, when the blade starts rotating, what happens? Blades are mounted on a shaft, so shaft will also start rotating. Okay, and see, when that shaft it rotate inside a north and south pole, okay, or inside armature winding, what happens? Okay, power gets produced. Okay, because it is further coupled to generator, right? Then power will be produced. So this is how we are producing a power by using a vapor. Okay, because boiler was producing a vapor or steam which was supplied on the blades of the turbine, which has produced a power. That's why it's called as vapor power cycle. Right. Now let us move to the gas power cycle. Gas power cycle. Okay. So gas power cycle. Okay, by using a gas. Okay, as like auto cycle. Auto cycle it's called as, okay, it's called as spark ignition engine. Okay, auto cycle it is used in spark ignition engine. Okay, when we talk about the diesel cycle, okay, it is used in compression engine. Okay, CI engine, it's called as compression engine. Okay, then one more cycle it's called as dual cycle. Okay, then there are a number of cycles like Breton cycle, like Stirling cycle, linear cycle, Piston cycle. Okay, so those cycles also we'll see. Okay, and next sixth module is a compressible fluid. Next module is a compressible fluid. So is that okay? Have you understood what content we will be covering through this course? Yes.
Yes, sir.
Yes, sir.
Yes, sir.
Yes,
Is that okay?
Yes, sir.
Yeah.
Yeah.
See. What I expected that, okay, you have passed the diploma. Okay, so some of the things you already know. Okay, basics you already know. Okay, now instead of taking more time in clearing the basics, okay, we will try to utilize that time what is expected in the degree, okay, in this course, which is in the direct second year. Okay, so okay, now I'll just move to the next point. Okay, now let us start with our module number 1. Okay, so see, this is somewhat theoretical module. Okay, so we'll try to understand, okay, give some more time in understanding this thing. Okay, so see, first, okay, let me explain you what is thermodynamics. Okay, so see, in thermodynamics what we'll do, okay, we will understand, okay, how the energy get transferred. Okay, how the energy get transferred. Okay, now see, for understanding how energy get transferred, okay, see, let me go with the basic definition. So thermodynamics, it's the science of energy transfer, particularly heat and work, and its effect on physical properties of the substance. Okay, by looking at the statement, you might not able to understand, okay, what the statement is. Okay, so thermodynamics, it's the science of energy transfer. Okay, so for that, first you understand what is energy. Okay, so see, energy, it is broadly classified as energy can be either heat or work. Okay, energy can be either heat or it can be work. Okay, so see, heat can be converted into work or work can be converted into heat. Okay, so that is the meaning of energy transfer. See, energy, what is energy? It is either heat or it can be work. Okay, that is energy. Energy is either heat or it is work. Now question is, what is transfer? What is transfer? What do you understand by transfer? Transfer means converting heat into work or work into heat. Okay, we are interested to do that conversion from heat to work and from work to heat. Okay, so in thermodynamics, what we will see, okay, the conversion of heat into work and work into heat, that we are able to, that in that term we are interested. Okay, but see, when heat get transferred into work or when work get transferred into heat, okay, the physical properties changes. Okay, the physical properties changes. Now which are those physical properties? All of you, which are those physical properties? Okay, so if you just take the properties, right, if you just take the properties like pressure, volume, temperature, right, these basic properties, you know, like pressure, volume, temperature. Okay, so when you convert heat into work or work into heat, what happens with the pressure? What happens with the volume? What happens with the temperature? Whether it increases or whether it decreases. Okay, or it remains constant. See, three cases are possible. Either it will remain constant, or it decrease, or it increase. Okay, so when heat get transferred into work, or when work get transferred into heat, okay, we are interested to know how it affects the physical properties like pressure, volume, temperature, whether it is increased, whether it's decreased, okay, or it remains constant. Okay, so such terms or such behavior, okay, we are going to see in the thermodynamics. Okay, so thermodynamics, it's a science of energy transfer. Okay, energy transfer means what? Either heat transfer or work transfer. Okay, and its effect on physical properties of the substance. Okay, okay, so when heat get transferred, again question, what is heat transfer? See, what is energy transfer? Energy transfer is heat transfer or work transfer. Okay, now you will get a question, what is heat transfer? Okay, so heat transfer, it's nothing but a, see, heat transfer, heat can be either received or it can be lost. Okay, so heat can be either received or heat can be lost. Okay, so when heat is received or heat is lost, it is said to be transferred. It is said to be transferred. Similar case is going to happen with the work. Similar case is going to happen with the work. Okay, work transfer. What do you understand by work? Work can be either produced. Work can be produced. Okay, if you just take the example of devices like engines, turbines. Okay, they are work producing devices. Okay, so such devices, they used to produce a work. But when we take about the example like pump, compressor, refrigerator, okay, they are basically work consuming devices. The reason is when you need to run a compressor, okay, you need to switch on the electricity supply. Okay, you need to supply the electricity to that. Okay, so that's why they are work consuming devices. Okay, so what do you understand by work transfer? Either work produced or work consumed. Okay, so see, whenever heat is transferred or work is transferred, properties are changes. Okay, property changes. Okay, so such behavior we need to check it. Okay, in the thermodynamics. Okay, now see.
So can you explain one more time?
Yeah, okay, no problem. Which concept of energy transfer?
Heat and work, the both.
Okay, let's see. That's the reason why I've just taken one example. Okay, as I told you, you just take a steel ball. Just take a steel ball which is at 100 degrees Celsius. We have a steel ball which is at 100 degrees Celsius. Okay, and we have water at 40 degrees Celsius. We have water at 40 degrees Celsius. We have a steel ball at 100 degrees Celsius. We have water at 40 degrees Celsius. Okay, now what we will do, we will put that steel ball into the water. Okay, we'll put that steel ball into the water. Okay, so let's say after 10 seconds, what will happen? See, steel ball, it is at a higher temperature. You can see what is the temperature of the steel ball? It's 100 degrees Celsius. When you put this steel ball, which is at 100 degrees Celsius, into the water, which is at 40 degrees Celsius, what happens? See, naturally, heat flows from high temperature to low temperature. Okay, this is what happens naturally. Heat naturally flows from high temperature to low temperature. Because see, if you want the heat to flow, there has to be a temperature difference. See, heat will flow only and only when there is a temperature difference. Okay, now see, when you talk about the temperature of the steel ball, it is 100. Temperature of the water is 40. Okay, so there is a temperature difference of 60. You can check. 100 minus 40 is 60. Okay, so there is a temperature difference of 60. Okay, see, there is a single temperature difference. Okay, that means there is a temperature difference of 1 degree Celsius, then only heat will flow. Okay, it doesn't matter how much temperature difference is. Okay, there is okay, what is the requirement? It's only the temperature difference. Okay, so see, there is a temperature difference of 60 degrees Celsius. Okay, so what happens? The steel ball will start losing the heat because it is at higher temperature. Steel ball which is at higher temperature will start losing the heat. Okay, what is happening with the water? Water, it is at lower temperature, so it will start receiving the heat. Okay, The steel ball which is at higher temperature will start losing the heat. Water which is at a lower temperature will start receiving the heat. So after 10 seconds, what happened is this 100 degrees Celsius got dropped to 90 degrees Celsius. 100 degrees Celsius got dropped to 90 degrees Celsius, while this 40 degrees Celsius got increased to 45 degrees Celsius. You might have observed. See, this got dropped by 10 degrees Celsius. This got increased by 5 degrees Celsius. It is not required that if steel ball has dropped the temperature by 10, the water should also increase the temperature by 10. It's not required. See, it will depend upon mass, it will depend upon specific heat, all those properties, right? So see, after 10 seconds, this got dropped to 90, this got increased to 45. Okay, but still there is a temperature difference. You can see there is a temperature difference of 45 degrees Celsius. So what happens again? After 20 seconds, 90 will drop to 80, 45 will increase to 50. Okay, still there is a temperature difference. You can check 30 degrees Celsius temperature difference. So after 30 seconds, what happens? This 80 degrees Celsius will drop to 70, and this 50 will drop to 60, increase to 60. 50 will increase to 60. Now still there is a temperature difference of how much degrees Celsius? 10 degrees Celsius. Now after 40 seconds, what will happen? This 70 will drop to 65, and this 60 will increase to 65, and this 60 will increase to 65. Okay, 60 will increase to 65. Now you can check. Now see, there is no any temperature difference. There is no any temperature difference. So what will happen afterwards? Okay, what will happen afterwards? Okay, now the steel ball will not lose the heat. Water will not receive the heat. Okay, so heat will not flow. So after this, heat will not flow. The reason is that steel ball and water have reached same temperature. So when they have same temperature, that means what? There is no temperature difference. And if there is no any temperature difference, obviously heat will not flow. So is that okay? Yes, is that okay, all of you?
Yes, sir.
Yes, sir.
Is that
Yes,
okay
sir.
or not? Let me know.
Yes, sir.
Okay,
Hello.
okay, no problem. No problem. Okay, so this is all about, okay, this is all about, it's all about what? Concept of, okay, thermodynamics. Okay, see, similar case is going to happen with the work. Okay, work. So if for work we will see it detail. For heat it's very simple in terms of temperature, but for understanding work, okay, we need to derive the formula how to calculate the work. Okay, then only you will be able to understand it. Okay, so this is all about thermodynamics. Okay, now let us move to the next point. Okay, what is called as thermodynamic system? Okay, what is called as a thermodynamic system? Now try to understand. Okay, so see, this thing you might have also seen in your diploma course. Okay, system. So system, how to understand what is system? What is system? Can anybody tell me?
Where the work is going.
Okay. Yeah, see, system is a specified region. Okay, it is a specified region or quantity of a
आपकी आवाज नहीं आ रही सर ये वॉइस इज गॉन सर
So your mic
Voice
has
नहीं आ रही. Sir, you are not audible.
योर माइक इज ऑफ सर
boundary. Okay, so instead of taking entire paper, I
Sir,
will just
your
select
mic.
only this part of the paper.
Sir, just a moment, sir. So your mic was off.
Now is it audible?
Now it is audible.
Yes, sir. Now you are audible.
Yeah. Okay, no problem. Now see, instead of studying the entire paper, this is basically the white paper. Okay, what I will do is I will study only the small part of that paper. Okay, because this small part of the paper, okay, it is having same properties as like other part, right? So there is no point in studying the entire paper. I will just study only the small part of the paper, and that small part of the paper, okay, will represent the entire paper. It will represent the entire paper. So that I will call it as system. Okay, now see, everything Okay, outside the system, it is called as a surrounding. Everything outside the system, it is called as surrounding. In simple, if you assume yourself as a system, okay, so everything except you, it becomes a surrounding, right? Everything except you is a surrounding, likewise, right? So this is the system, okay? Everything except the system, it's the surrounding, okay? And when you see this line basically separates the system from the surrounding, and it is called as a boundary. Okay, so boundary is basically the imaginary. Okay, see, when you talk about the boundary, it might be real or it might be imaginary. Okay, it's not necessary that boundary has to be real only. It might be real or it might be imaginary. So boundary, okay, it's basically separates the system from the surrounding. Okay, and when you talk about the system and surrounding in combined, okay, it gives rise to universe. Okay, and system plus surrounding combined, it is called as universe. Okay, so that is what is called as. Okay, so this the system. Okay, system is basically what? A region on which you are focused. Everything except it's a surrounding. Okay, and the line which separates the system from the surrounding, it's called as boundary. Okay, so this is all about the basics of thermodynamics. Okay, now see, in thermodynamics, okay, there are two approaches. In thermodynamics, there are two approaches. Okay, first it's called as macroscopic. Okay, try to understand this one. Macro, MAC. Okay, understand. Macroscopic approach. Okay, now what is this approach? Okay, by looking at the diagram. Okay, now see, if you might feel that, sir, you are just posted the page. Okay, now see, this content, it is already covered. This diagram or pages, everything is being drawn by me during the lectures which are taken for the second year. Okay, now by tomorrow they will be finishing their semester. Okay, so instead of drawing this diagram again, I find that let us give some time in understanding it. That is the reason why I am not writing or drawing this diagram again. Okay, but when we'll start with the derivation, okay, we need to derive those. Derivation and numerical, we need to solve those. Okay, so for some initial part, theoretical part, I will be explaining it. Okay, so let us start with macroscopic approach. Macro, MAC, macroscopic approach. Okay, now see what macroscopic approach is. Okay, now see, simple. Okay, we have this pot. Okay, we have water. Inside the pot, we have water, and see, that water, it is at a certain temperature. Okay, now I need to determine the temperature of the water. Okay, which is inside the pot. Okay, so how will determine? I will simply take a thermometer. I will dip that into the water, and I will measure the temperature. Okay, so this is called as macro. Okay, MAC, macroscopic approach. Now, what do you understand from this? Okay, you have assumed the entire system as a single system. Okay, whatever the volume of the water it is inside the pot, that you assume as a single system. Okay, so this is called as a macro, MAC, macroscopic approach, and this is basically classical approach, or it's a traditional approach. Okay, it's a traditional approach. Now let us go to the microscopic. Approach. Now, what is microscopic approach? Now see here, all of you. See, same diagram I have. Okay, I have a pot inside which, okay, we have water. Okay, now see, instead of dipping a thermometer, okay, and measuring the temperature for entire volume of water, what we'll do? Okay, we will just divide this into number of parts. You can see here, we'll divide this into number of parts. Okay, and we will measure the temperature for every part. And then we'll take the average of all those temperatures. Okay, and that is called as microscopic approach. Is that okay? That is called as microscopic approach. See, in macro, that is in the first case, what we have done, we are just simply insert the thermometer, measure the temperature, Okay, and it was for total volume. It was for total volume, right? Now here in microscopic, what we are doing is we are dividing that liquid into number of small parts. We are measuring the temperature of every part, and just then we are taking the mean or average. Okay, and that will give me the temperature. Okay, so that is called as microscopic. See, when you talk about micro, it's a statistical approach. Okay, and or you can call it as recent approach. Okay, so this is a recent approach. So is that okay, all of you?
Yes, sir.
Is that okay?
सर इसके अलग अलग पार्ट को मेजर कैसे करेंगे?
Yes, yes. See, now see, there are certain advanced techniques how to measure it. Now see, there are certain techniques. Okay, there are certain techniques. Now you might have doubt, na? So how to separate that? How to separate that?
Yes, sir.
Right? So see, we may insert some restrictions, okay, or we may limit them to certain volume, okay, and then we can measure it. Okay, we might make some compartments for that, and then we can measure, right? Is it okay?
Yes, sir.
So now let us move to the next point. Okay, what is called as types of systems. Okay, see, in general, you understand there are basically three systems. One is a closed, second is open, and third is isolated system. Okay, closed system, second is open, and third is isolated system. Right? See, and we are more focusing on closed and open. Okay, we will not go for isolated system. Okay, the reason I will let you know afterwards. Okay, now let us start with the first system that is called as closed system. Okay, see, closed system, you understand? Closed system, it's a non-flow system. Closed system, it is called as non-flow system. The reason is, okay, let us take the example. Let us take this example. Let us consider this cylinder. This is cylinder. Okay, this is basically piston. Okay, the hatch lines which are shown, that is a piston. See, this is cylinder. Okay, which is and above there is a piston, and inside which we have some gas which is filled. Okay, inside which we have gas, it is fixed. Gas is filled. Sorry, gas is filled inside that piston and cylinder arrangement. Okay, inside a piston and cylinder arrangement, we have this gas filled. Okay, now see, all of you see here. See, whatever the mass of the gas which is present inside this system, it is same. It is same. You have observed for this particular system, there is no inlet port, there is no outlet port. Okay, so whenever it's a closed system, there is no inlet, there is no outlet. Okay, so there is no point of exchanging the mass, right? Mass will not enter, mass will not leave. Okay, see, whenever there is an inlet port and outlet port, okay, when we want some fresh fluid to come inside, when we want the exhaust fluid to go outside, that is the reason why we require inlet and outlet. See, purpose of the inlet is to take a fresh air or to take the fresh fluid, and purpose of the outlet port is to exhaust the flue gases, okay, or the exhaust fluid, right? So if you see this diagram, there is no inlet, there is no outlet. Okay, so whatever the mass that is present here, it is constant. Mass is constant. Okay, because no inlet, no outlet. Mass is constant. Okay, so what we are doing is, whatever the gas that is present inside, we are heating that gas. We are heating that gas. See, I will repeat it. Okay, we have piston cylinder arrangement where we have a gas which is filled inside. Okay, and that gas we are heating with the help of burner. Okay, so when we heat that gas, what happens when we heat that gas? Okay, the gas which is present inside the piston cylinder arrangement, it will start expanding. Okay, it will start expanding. See, when we heat it, what happens? Energy get released. Whatever the energy that is present inside a gas will be get released. And when energy get released, okay, that is basically called as expansion. Okay, what happens? Okay, the gas which is present inside will exert some force on the piston, right? This gas which is present inside, okay, it will be obviously, it will be at a certain pressure. Okay, the gas which is present inside, it will be at a certain pressure. Okay, and when that pressure will act on the piston area, okay, when that pressure will act on a piston area, it will give rise to force. Okay, what is force? Force is pressure into area. So gas, it is at a certain pressure. When the gas, it is at a certain pressure, when it will act on the piston area, it will give rise to force, and that force will cause the piston to move upward, right? That force will cause the piston to move upward. Okay, that, see, what I need to convey here is, see, all of you are supplied the heat. Okay, you supplied the heat with the help of burner, and that heat get converted into work in the form of movement of the piston, right? See, what you supplied? What you supplied? You supplied heat. Okay, and when you supplied the heat, what happens? The energy which is present inside the gases gets burned or gets released, and when the energy gets released, okay, the gas will exert some force on the piston. As a result, the piston has moved. Okay, that means what? See, when the force is causing some displacement, it is called as work. Whatever the force that is acting on the piston, it is causing the displacement of the piston. Okay, so when force acting on a piston, it causes the displacement of the piston. Okay, then force multiplied by displacement, it is nothing but a work. What you got? So how much work that is being produced by the piston? It is force which is exerted on the piston multiplied by what is the displacement of the piston. What is displacement? The distance through which the piston has moved. Okay, let's say piston has moved like this. Let's say it has moved 2 centimeters. So 2 centimeters, it is nothing but a displacement. Okay, so when we supply the heat, it gets converted into work. Okay, when we supply the heat, it gets converted into work. Okay, that means, okay, work, energy get transferred. Okay, energy was transferred in the form of heat, and it got converted into work. Okay, so energy got transferred from heat to work. Energy got transferred from heat to work. But what was happened with the mass? Okay, what was happened with the mass? Mass is constant. You can check. Mass is constant. See, we are not taken fresh air. We are not exhausted the, okay, used air or used fluid. Okay, so that means mass is constant. Okay, but energy can enter and energy can leave. See, mass is constant. You can check. Mass is constant. Now you might have a question, sir. Mass is constant, but volume has changed. Volume has changed, right? Now see, mass is constant. It doesn't mean that volume should also remain constant. Volume may increase or it might be decrease. Volume may increase or it might decrease. Right? See, volume may increase, volume may decrease. Okay, but what is about mass? Mass is constant. Right? See, the volume will depend upon mass. Mass will not depend upon volume. Try to understand. Okay. So here, when you see in the diagram, energy has entered in the form of heat and it is leave in the form of work. Energy entered in the form of heat, leave in the form of work. Right? So such system, it is called as closed system. Okay. Mass is constant. Mass is constant. Mass doesn't change. But what is about energy? Okay. Energy can enter or leave. Okay. So in simple, mass cannot enter or leave. Mass cannot enter or leave, but energy can enter or leave. Right? Mass cannot enter or leave because no inlet and no outlet, but energy can enter or leave. So in this diagram, energy has entered in the form of heat and it has lived in the form of work. So that is called as closed system. Closed system, it is also known as non-flow system. It is called as non-flow system. Okay. So or it is also called as control mass. It is called as control mass. The reason is mass doesn't change or mass cannot enter or leave. That's why it's called as closed system. Is that okay? Yes, is that okay?
Yes, sir.
Okay. Now let us go to the next point. That is called as open system or flow system. Try to understand now. Open system and flow system. Okay. Now see, you might have observed the difference between above diagram and the below diagram. Above diagram and the below diagram. Okay, just see what is the difference. Okay, here you can see there is an inlet port and there is outlet port. Okay, so in the inlet we see this diagram. It's basically for the boiler. Okay, I have not written it. Okay, but this diagram it's basically for the boiler. Now see, the purpose of the boiler is to generate a steam. Okay, what is the purpose of the boiler? It is to generate a steam. So at the inlet to the boiler, we are supplying a water. We are supplying the water. So when we supply the water in the boiler, okay, so water means what? Okay, there is certain mass. There is certain mass is there. Okay, so water we have supplied. Okay, when we supply the water in the boiler, okay, so in the boiler we are adding the heat. So when we add the heat, what happens? Okay, the temperature of the water will start increasing, and when the water reaches its saturation temperature, water gets converted into vapor, right? Water gets converted into vapor, right? So water gets converted into vapor. Okay, so as you can see above you might have observed the vapor form. Okay, now again, whatever the vapor form, okay, so whatever the vapor form, it is either wet or it is dry. Okay, so it might be wet steam or it might be dry steam. What do you mean by wet steam? The steam which is wet. Okay, the steam which is wet, that means it contains some moisture particle or liquid droplets. That is called as wet steam. And what is a dry steam? Dry steam is a steam which does not contain any moisture. Dry steam is a steam which does not contain any moisture. That is called as a dry steam. Okay, now see, when you need to operate or when you need to supply the steam to any thermal power plant, the steam has to be dry. The steam has to be dry because see, when you supply wet steam, okay, in the thermal power plant, and if you allow that wet steam to flow on the blades of the turbine, what happens? The blades of the turbine gets, okay, corroded. Okay, they undergo corrosion. Basically, they corrodes. Because see, wet steam, it's nothing but a liquid droplets. And if these liquid droplets are going to segregate on the blades of the turbine, okay, there will be erosion. And whenever there is erosion, okay, life of the turbine blades get reduced. That is the reason why steam, okay, when you need to supply the steam, it should be either at least dry. It should be at least dry. Now you might have a question, why you're asking at least? Okay, the steam should be at least dry or it should be superheated. It should be superheated. Now what is superheated? Now see, when you talk about the current pressure is atmospheric pressure, and that is 1.013 bar. That is atmospheric pressure. If you start heating the water at 1 atmospheric pressure, it begins to boil at 100 degrees Celsius. It begins to boil at 100 degrees Celsius, right? So see, when you start heating the water above 100 degrees Celsius, it is said to be superheated. It is said to be superheated. That means it's a superheated steam. So superheated steam is the steam whose temperature is greater than the saturation temperature. Okay, so at 1 atmospheric pressure, okay, at 1 atmospheric pressure, our saturation temperature is 100 degrees Celsius. So if you have the steam above the 100 degrees Celsius, it is said to be superheated. Okay, but this is applicable only for a 1 atmospheric pressure, right? So these are the types of steams. Okay, let us now come to this point. Okay, so this is inlet, this is outlet. So at the inlet we have water, at the outlet we have steam. Okay, so see, it is not possible directly to convert water into steam. We need to supply some heat. Okay, so see, we have supplied the heat. That is the reason why, okay, water get converted into steam. Okay, that means mass is entering, at the same time mass is leaving. Mass is entering and mass is leaving, right? Mass is entering in the form of water, it is leaving in the form of steam. Okay, that means mass is entering, okay, as well as energy is entering and leaving. Try to understand. Mass can enter or leave, at the same time energy also can enter or leave. Okay, how the energy is leaving? energy it is leaving in the form of heat. Energy is entering in the form of heat. It is leaving also in the form of heat. Okay, so you are supplying the heat to the water, so water gets converted into vapor. Okay, and that vapor is carrying the same heat. The vapor is carrying the heat. Okay, so you are supplying the heat. Okay, that means you are the energy it is entering in the form of heat. It is also leaving in the form of heat. What is about mass? Mass is also entering. Mass is also leaving. Right. So see here, all of you. Here, what is constant is mass flow rate is constant. See, this is very important. In case of an open system, mass flow rate is constant. Mass flow rate. Try to understand what is rate. Okay, what is rate? See, in case of a closed system, we used to take it mass. In case of a closed system, we used to take it mass. Okay, mass is in kg. Mass is in kg. So for closed system, we need to take only mass, and that is in kg. But when we talk about the open system, we need to take mass flow rate. How much mass is entering per second? Okay, so with the same rate, the mass should leave. I will give a simple example. Let's say 4 kg of mass is entering per second. So at the same time, 4 kg should leave per second. Okay, let's say 4 kg is entering per second. So similarly, 4 kg should leave per second. Okay, if see, this is required. The rate at which the mass is entering, with the same rate, the mass should leave. This is required so as to maintain the continuity. Otherwise, what will happen? Let's say if the mass is entering with the 4 kg per second and mass is leaving with the 2 kg per second, what will happen? There will be discontinuity in the flow. Some fluid will be get segregated inside a system. Okay, that should not be. Okay, so the rate at which the mass is entering, with the same rate, the mass should leave. Okay, the mass is entering, the mass is leaving. Okay, that is called as mass flow rate. Okay, so mass is entering at the 4 kg per second, it should leave with the same rate, that is 4 kg per second. But remember, the rate at which the mass is entering, with the same rate the mass should leave, that is called as the open system. Right? So for open system, we have inlet and outlet port. Okay, on the condition that the mass flow rate is constant. So energy is also entering, energy is also leaving. Okay, so all of you see here, in closed and open system, in both the systems, energy is entering and energy is leaving in both the system. But what is the difference between closed and open? In closed system, mass is constant. In closed system, mass is constant, while in case of an open system, mass flow rate is constant. Okay, in closed system, mass is constant. In open system, mass flow rate is constant. Is that okay? Yes, is that okay? All of you.
Yeah.
Okay,
Yes,
sir.
sir.
Yes,
So
sir.
all of you can respond. You can respond. There is no problem. Right? So this is all about the types of the systems. Is that okay, all of you? Let me know.
Yes, sir.
Yes, sir.
Okay. Now let us go to the next point. Let us go to the next point. Okay. Now let us see. Okay. Third system. Okay. Third system. It's basically called as isolated system. Third system. Okay. Third system. It is called as isolated system. See, now what is isolated system? Okay. See, in isolated system, okay, neither mass nor energy can enter or leave. Okay. Simple example. With the example, I'll okay, let us take a thermos flask. In that, let's say you pour 1 liter of tea. Okay, let us pour 1 liter of tea. Okay, let us pour 1 liter of tea. Okay, I think someone has annotated it. Okay, I need to clear. Okay, now see, let us see what is isolated system. As I told you, you just take the example of thermos flask. In thermos flask, what do? You pour a tea you pour 1 liter of tea, which is at 100 degrees Celsius. You pour 1 liter of tea at 100 degrees Celsius. I think Safwan Duste, right? Is there any doubt? Safwan, is there any doubt? Because you have some annotated. Shall I clear that? I'll clear that. Because I have not yet started with this content. Okay. So let us take a thermos flask. In a thermos flask, okay, let us pour a tea, 1 liter of tea, which is at 100 degrees Celsius. Let us pour that at 100 degrees Celsius. Okay. Now what you can do after 10 minutes, let's say after 10 minutes, okay, what do? You measure the quantity of the tea. At the same time, you measure the temperature of the tea. What will happen? Temperature of the tea, you will find it is same as before, as which was before a 10 minutes, right? That means temperature has remains constant. That means heat is not lost. Heat is not lost. See, if the temperature got dropped down, that means what? It is lost. And that is not the purpose of thermos flask. Purpose of the thermos flask is to keep the tea hot. Okay. So when you measure the temperature after 10 minutes, you will find the temperature it is same as before. Okay. So that means there is no heat lost. What do you mean by no heat lost? There is no energy transfer. There is no energy transfer. At the same time, okay, whatever the mass of the tea, okay, you will find it is same. Mass of the tea, you will find it is same. Okay, so that is called as isolated system. See, so in isolated system, there is no mass transfer or there is no energy transfer. That is called as isolated system. Okay, but see, okay, there is no use of such system. Okay, there is no use of such systems. Okay, so what we'll do, okay, we will study in detail either for closed or for open system. Okay, we will study either both the system will study, that is closed system and open system. We will not see isolated system, because with isolated system, you are able to do nothing. Okay, you can't do anything with isolated system. Okay, now again, in case of an closed and open system, okay, every engineering application, it's open system. Okay, every engineering application is an open system. So again, out of closed and open system, we will go in detail for the open system, because when we talk about any engineering application, compressor, okay, refrigerator, pump, turbine, heat exchanger, boiler, condenser, any device you take, it works on which system? Open system. So we will see that. Okay, so is that okay with the isolated system?
Yes, sir.
Okay, so this is called as isolated system. Okay, now see one more point, it is called as thermodynamic properties. Okay, one more point it is there, that is called as thermodynamic properties. Now what is thermodynamic properties? Now say try to understand. See, what do you understand by properties? So see, properties determines the physical state. Determine the physical state. Now simple. If I told you that, let's say the temperature of the water is 100 degrees Celsius. Temperature of the water is 100 degrees Celsius. So from that, okay, you understand that water is hot. Right? Water is hot. If I say that temperature is 100 degrees Celsius, so you click that the water is hot. Okay, so you will not check the temperature physically directly, right? You will not put a hand and you will not check. You know that it's hot, right? Similarly, if I say that the temperature of the water, it's okay, let's say 10 degrees Celsius. Temperature of the water is 10 degrees Celsius. You will understand that the water is cold, right? Water is cold or cool. Water is cool, right? So see, when I give you the temperature, okay, you are able to understand whether it's hot or cold. So that means you are able to understand the physical condition, whether it's a hot or cold. So that is the significance of the properties. So properties determines, okay, the physical condition of the system. Okay, so there are two properties, or there are two or broad classification of the properties. One it is called as intensive and second is called as extensive. Okay, one it is called as intensive property and second it is called as extensive properties. Now what is intensive? Okay, try to understand what is intensive. See, as the name indicates, okay, I is intensive. So in the same manner, it is independent. Intensive is independent. Okay, so intensive properties are independent of mass. That means these properties doesn't depend on mass. Okay, intensive properties doesn't depends on mass. So which are the properties? Okay, like pressure. Let's say pressure. Let's say temperature. These properties, they doesn't depend upon mass. Simple example. Okay, now let us now you are sitting at your home. Okay, in your room. Okay, you measure the pressure, right? You measure the pressure, what is inside your room. Okay, now let us say you go outside the room and you measure the pressure. You find that the pressure will be same. It doesn't depend what mass you have inside. It doesn't depend what mass you have outside. Okay, pressure you will find it to be same. Similar thing you can have a temperature. Okay, let us say, see, out of 1 liter of tea, which is at 100 degrees Celsius, okay, let us take 20 ml. Let us take 20 ml from that, and let us measure the temperature of 20 ml of tea. Okay, you will find it is same as 1 liter of tea. Okay, because we have 1 liter of tea at 100 degrees Celsius. And out of 1 liter of tea, I have taken 20 ml and I just measure the temperature. Okay, you will find that temperature is same. It is 100. It will not depend upon mass or those, right? So is that okay, all of you? So this is called as intensive. So properties like pressure, temperature, they are basically the intensive properties. Is that okay? Yes, is that okay?
Okay, sir.
Okay. Now let us go to the next point, that is called as extensive properties. Extensive properties. Right. Now see, extensive properties. The properties will depend upon mass. The properties which will depend upon mass. Okay. Now just see, I have written the properties like volume. Okay, volume will depend upon mass. I repeat, volume will depend upon mass. Mass will not depend upon volume. Okay, mass. Okay, volume will depend upon mass, right? So volume it's dependent on mass. Volume is a dependent on mass, right? So that is called as extensive properties. Okay, one more property, it is called as enthalpy. Enthalpy. Okay, now see, at this stage you might not be able to understand enthalpy. Okay, what is that? Okay, in the next 2 or 3 lectures I will let you know enthalpy. So see, enthalpy, remember, enthalpy it's the addition of, okay, enthalpy it is indicated by H. It's the addition of U plus PV. Okay, enthalpy it's the addition, or formula is U plus PV. U is called as the internal energy and PV, okay, it's a pressure and volume. Right, so this is the definition for enthalpy. Okay, now second is entropy. Entropy. So entropy, concept of entropy we will see in the second module. Now you try to just remember it, that entropy is the extensive property. Okay. Next thing is internal energy. Now what is internal energy? Okay, this you will see, okay, in this module only. Now in next 2 to 3 lectures we'll see. Okay, so enthalpy and internal energy, this term enthalpy and internal energy we will see in next 2 to 3 lectures. What is entropy? For that we need to go to module number 2. Okay, that will be covered later, right? So these are the extensive properties. Right? Now see, all of you, see, when we talk about the volume, okay, it is indicated by capital V. All of you know, volume it is indicated by capital V, and unit is meter cube. Volume is indicated by capital V, and its unit is meter cube, right? When you talk about the enthalpy it's nothing but energy, right? So its unit it is in kilojoule. Enthalpy it is indicated by capital H, and its unit is kilojoule. When you talk about entropy, see, for entropy the formula is Q by T. Try to understand. Formula for entropy is Q by T. Okay, Q will be in kilojoule. Okay, and temperature is in Kelvin. So it's kilojoule per Kelvin. Now see, why I'm not going in detail? Because if I told you that the entropy is Q by T, then you will ask me, sir, why it is Q by T? For that, I need to again go refer the entire derivation. Okay, so that we will see progressively. Not a problem. So entropy, it is indicated by kilojoule per Kelvin, and internal energy it is in kilojoule. Internal energy, it is in kilojoule. So see, internal energy is the energy which is stored within the system. Internal energy, it is stored within the system. Okay, and it is indicated by kilojoule. Now see, all of you. Now this is the important concepts. Okay, that you're supposed to understand now. Okay, volume, it is indicated by V, whose unit is in meter cube. Okay, now we need to see what is specific volume. Okay, we are just adding one word. Okay, what is called as a specific. Okay, so see, volume V, which is indicated in meter cube, if you want that to be in specific, okay, so see, what is specific? In specific, we will divide every term by mass. In specific, okay, we will divide every quantity or every property by mass. Okay, so what we'll do, when we divide this volume by mass, it becomes specific. Okay, so initial volume was V. Okay, volume was V. I divided this by mass. I have divided this by mass. So it becomes specific volume, and it is indicated by small v. See, volume, it is indicated by capital V. Okay, specific volume, it is indicated by small v. Okay, specific volume is indicated by small v. Now, how to get small v? That is specific volume. Okay, you just need to divide the total volume by mass. You need to divide the total volume by mass. So total volume, it is indicated by meter cube, and mass is in kg. Okay, so unit is meter cube per kg. So unit is meter cube per kg. Is that okay? Have you understood?
Yes, sir.
Okay.
Yes, sir.
Now let us exercise same for the enthalpy. Enthalpy, it is indicated by H. Enthalpy is indicated by H, and unit is in kilojoule. Enthalpy indicated by H, unit is in kilojoule. Now I want it to be specific enthalpy. I want it to be specific enthalpy. Simple, you divide by mass. Okay, so when we divide capital H, okay, I'll just, okay, you can see here. Okay, so okay, as you can see, when we divide this specific, okay, enthalpy that is H by mass, that is small m, okay, then that enthalpy, it becomes specific enthalpy, which is indicated by small h. Okay, and unit, you can see, it is kilojoule per kg. Simple here. Whatever the meter cube is there, you divide it by kg. Okay, and the letter which are written, okay, in the capital, you need to write down it as a small letters. So those properties become specific. Okay, see, in units you divide by kg. Okay, and their letters, okay, or their notations become small. Okay, so this is small v, this is small h, this is small s, this is small u, because they are specific. How we got specific? By divide the total terms by mass. See, specifics means what? They are available for 1 kg. See, this much volume is available for 1 kg. This much enthalpy is available for 1 kg. This much entropy is available for 1 kg. This much internal energy is available for 1 kg. See, obviously, okay, we should know everything for 1 kg. Okay, and let's say we have 5 kg mass, then multiplied by 5. Okay, then you will get that 5 kg of mass. See, everything we should know for 1 kg, and in the, as per problem, let's say we have requirement of 5 kg. Then whatever the answer that we got, you multiplied by 5. Then you will get that total volume for that particular kg of mass, right? So this is what we are doing. So is it okay with this specific concept?
Yes, sir.
Is that okay, all of you?
Yes,
See,
sir.
I'm asking to everyone.
Yes, sir.
You can just meanwhile tell me. You can then
Yes, sir.
immediately
Yes,
unmute yourself. Okay. So now let us move to the next point. Okay. See, all of you see this one. Okay, there is a next point that is called as Pdb work. Okay, Pdb work. Okay, this is also known as displacement work. Okay, or this is also known as moving boundary work. Okay, see here, Pdb work. This Pdb work, it is also known as displacement work, or it is also known as moving boundary work. So see, all of you just try to understand this one. Okay, so see what we have here is we have this piston and cylinder arrangement. You can see this the region which I've hashed. Okay, this is basically the piston. Okay, this is a cylinder, and inside this piston and cylinder arrangement, what we have some gas which is filled inside. Okay, which we have a gas which is filled inside, and the gas we have, okay, which is at a certain pressure P. The gas, it is at a pressure P. Right, now see, all of you know that piston always move between top dead and bottom dead. Is that okay? Because see, for any engine, okay, there are two centers. One is called as top dead and second is called as bottom dead. Piston always move, okay, between top dead and bottom dead center, right? So see, piston always move between top dead center and bottom dead center. Okay, and when the piston moves from top dead to bottom dead, whatever the distance that is traveled, the distance traveled by the piston between top dead and bottom dead, that is called as stroke. Okay, that is called as stroke. Okay, so whatever the distance that piston travel from top to bottom, it's called as stroke. Okay, that is called as stroke of the piston. Okay, so now let us come to this point. Okay, so we have a piston cylinder arrangement where we have a gas which is filled inside, and the gas it is at a pressure P. Okay, now you can see this piston, it is connected to, okay, connecting rod and further to crankshaft. You can see we will not go in detail in construction and working. Okay, but for the purpose of understanding, let us see this in a brief. Okay, this piston, it is connected to connecting rod followed by crankshaft. Okay, so what happens? Okay, so whatever the gases which are filled inside, or which are the gases which are present inside, okay, when they start expanding, what happens? The piston will start moving on the right hand side. Okay, when the gases will start to expand, the piston will start moving on the right hand side, right? So what happens? See, this is the initial position of the piston. You can see this is the initial position of the piston. Okay, now this is the final position of the piston. You can check in the diagram, because the piston has moved on the right hand side. See, as the gas will start expanding, the piston will start moving on the right hand side. So piston will move. Obviously, the crankshaft, okay, will also move, and crankshaft will rotate a crankshaft. Okay, so you can see initial. This is the position of connecting rod. This is the crankshaft. Okay. Now when the piston has moved distance dx, how much the distance has traveled by the pistons? The piston has traveled distance dx. So when the piston travels distance dx, what happens? You can see, okay, this okay, the crankshaft has rotated by angle. You can see this is the angle which has rotated. Okay, that means what? We are basically converting reciprocating motion of the piston into rotary motion of the crankshaft. Okay, reciprocating motion of the piston, we are converting into, okay, rotary motion of the crankshaft, right? So that is the purpose of the engine. Okay, that is purpose of the engine. Okay, see, the engine, it is converting heat into work. Okay, that means reciprocating motion of the piston, we are converting into rotary motion of the crankshaft. Okay, now see, so during this, the piston has moved how much distance? The piston has moved distance only dx, only small part of we have seen, only small part of the process we have seen. And during that small part, the piston has moved distance dx. Okay, but I repeat, but the piston will not move only dx. It will move between top dead and bottom dead. It will move from extreme left hand side to extreme right hand side. It will move from extreme left hand side to extreme right hand side. That means it will move the distance equal to length of stroke. It will move the distance equal to stroke. So dx is the small part of the stroke. You can call it dx is the small part of the stroke. Okay, Now let us do that. Now how to calculate? Okay. Now see, what is the force? What is the force that is exerted by the gas? What is the force that is exerted by the gas on the piston? How to calculate force? Okay. In order to calculate the force that is exerted by the gas on the piston, force is given by, you know, it's a pressure into area. Okay. So if the gas is at a pressure P, okay, if the gas is at a pressure P, and if that pressure P, it is acting on the piston area A, if the pressure P, it is acting on the piston area A, then what is the force exerted by the gas on the piston? It is given by, force is given by pressure into area. Force is given by pressure into area. Is that okay?
Sir, please explain that distance dx.
Yeah. Okay. Now see, when this force will act on the piston, what happens? Where see, whatever the gas which is present inside, it is having pressure P, right? It is having pressure P. And what happens? That pressure P, it is acting on the piston area. Okay, that pressure P, it is acting on a piston area. Now see, piston area. Now here in the diagram, I have not shown the piston area. You know that piston it is in a circular shape. Okay, when you observe the cross section of the piston, it's circular one. Okay, so this pressure P will act on that circular area A. Okay, so when the pressure P will act on the circular area A, okay, then what is the force exerted by the force exerted due to the pressure P? Okay, force exerted is given by pressure into area. Say yes or no? Let me know. Is that okay?
Yes.
Force exerted, it is nothing but pressure into area. Right? Okay. Now when this force is exerted, what happens? When the force is exerted, the piston will move through a small distance dx. The piston will move through a small distance dx. I am repeating, piston will not move only dx. It will move from top dead to bottom dead. So between top dead and bottom dead, we have considered a small distance dx through which the piston has moved. Obviously, this dx we need to integrate. This dx we need to integrate for a stroke. See, when we integrate dx, okay, what we will get? We will get a stroke. Stroke that is nothing but a length. Stroke we used to integrate by L. Okay, so integration of dx is nothing but integration of dx. It is nothing but the distance between top dead and bottom dead. That is called a stroke. Is that okay? Let me know. Is that okay?
Okay.
Now see how to calculate force. Force is given by pressure into area. Now see, when the force is exerted, there will be the displacement dx. This force is causing the piston to move through distance dx. Okay, this force is causing the piston to move through distance dx. Okay, so listen, when the force is causing displacement, it is called as work. Is that okay? When the force is causing the displacement, it is called as work, right? Force is causing a displacement, it is called as work, right? So how to calculate work done? Okay, so work done during this small process, okay, I will call it as del W. I will call this as a del W. Okay, now why it is del W? I will let you know. You might have questions, sir, it is to be written as dW. For a small process, as like dx, it has to be dW. Okay, why are not written as a dW, and why are written as a del W? Okay, I will let you know immediately in this lecture only. Okay, now let us focus on this. So work done, that I have indicated by del W. Okay, during a small piston movement dx. Okay, work done during a del W during a small piston movement dx is given by, see how to calculate work. Work is given by, you know that, force into displacement. Work is given by, you can check. See, work is given by force into displacement. Okay, you can see this one. All of you, can you see this one? Work is given by force into displacement. Let me know. Yes, can you see this one? Work is given by force into displacement. All of you, can you see? Work is force into displacement. Del W is force into displacement. Now what is force? What is force? We already know it's pressure into area, right? Force is given by pressure into area, right? So force is pressure into area. I've written as it is. So pressure into area as it is, okay, into dx. See, work is force into displacement. Now what is force? Force is pressure into area. Force is pressure into area into dx as it is. Okay, now see here. So pressure again I have written as it is. Pressure I have written as it is. Now what is area into wall? Area into thickness. Area into thickness is nothing but a volume, right? Area into thickness or area into length is nothing but a volume. So A into, see, force I have written as pressure into area, and area into thickness I have written as volume, that is small volume. A into dx is dv. A into dx is dv, right? So what I got is, I got the formula, okay, for del w as p into dv. Okay, so how to calculate the work done? How to calculate work done? Work done del w is given by p into dv. Work done del w is given by p into dv. Is that okay? How I got the formula p into dv? Yes.
Yes, sir.
Yes, is that okay? See, because see, what is work? Work is force into displacement. Now, what is force? Force is pressure into area, right? So, work is force into displacement. Force is pressure into area. Now, what is area into thickness? Area into thickness is volume. Okay, that is dV. Now, see, all of you see, del W is the work done when the piston has moved distance dx. Okay, when the piston has moved distance dx. But I repeat, piston doesn't move only distance dx. The piston will move from top dead center to bottom dead center. Top dead center I indicated by 1, bottom dead center I indicated as 2. So I need to calculate now work done during process 1 to 2. See, I have done it for which process? Only for dx, only through distance dx I have done. But I want the work done when the piston will move from point 1 to point 2. I want that. Okay. So what we need to do? We just need to integrate this equation. So for I will integrate this equation. So integration 1 to 2, integration del W for process 1 to 2 is equal to integration Pdv for process 1 to 2. Simple. I just only integrated the equation for process 1 to 2. Is that okay? Is that okay or not? Let me know.
Yes, sir.
See,
Okay,
nothing
sir.
else I done. I just integrated that thing. Right? I just integrated. So I just integrated it. So now integration of del W. See, integration of del W. What is the integration of del W? See, what is del W? Work done during small process. Del W is small work done during small process. Then what is integration of del W? Integration of del W, it is nothing but work done during total process. That is for 1 to 2. Okay. So integration of del W I written as what? Work done during 1 to 2. Okay. Del W it is for a small process, but when you integrate small process, okay, it becomes a total process, that is during 1 to 2. Okay. So that is work done during 1 to 2 is given by integration Pdv 1 to 2. Okay. Now see, this formula I have not integrated it. You can see integration of del W I have written as W1 to 2. Integration of del W I have written as work done during 1 to 2. Okay. But integration Pdv for 1 to 2 I have written as it is, integration Pdv 1 to 2. Because this formula may change, this formula will change as per the processes. Okay, it might be constant pressure, constant volume, constant temperature, constant entropy. Okay, so based on the formula we need to modify, sorry, based on the process we need to modify that formula. Is that okay? So this is general formula. You remember, work done is integration of Pdv. Work done, it's the integration of Pdv. So this basic formula you remember. Okay, this basic formula you remember. Now see, now let us go. What we can extract from this formula? What we can extract from this formula? Try to understand. Okay, so have you understood the formula? How the formula came? Work done is integration Pdv. Have you understood how the formula came?
Yes, sir.
Okay. Now see, let us see, or let us try to extract, okay, some of the terms from the formula. Okay, now see, all of you see. Okay, now see, this process 1 to 2, okay, the process 1 to 2 of the piston, okay, I will plot on a PV diagram. In PV diagram, see, this is the first diagram which I have plotted. Okay, so see, in thermodynamics, we are morely focused on the PV diagram and TS diagram. TS diagram. Okay, we are majorly focusing on PV diagram. P is a pressure, V is a volume. Okay, pressure volume diagram and TS diagram, that is called as temperature entropy diagram. Temperature entropy diagram. Now let us focus on the PV diagram. Let us focus on the PV diagram. Okay, now see, the process 1 to 2, what happens? See, during when we move from process 1 to 2, what happens? As you can see, from process 1 to 2, what happens? See, this is the initial condition and this is the final condition. I repeat, this is the initial condition and this is the final condition, right? So when we move from point number 1 to point number 2, what happens? Pressure decreases and volume increases. Whether all of you agree to this one? Yes. Are you agree with this one, all of you? When we move from point number 1 to 2, what happens? Pressure decreases and volume increases. Okay.
Yes, sir.
So same process 1 to 2 I have plotted on a PV diagram. See, this is my initial state number 1. Okay, initial state is 1. Okay. Now I need to move to state number 2. Okay. But when I move from state number 1 to state number 2, what will happen? The pressure will goes on decreasing. So as pressure decreases, volume increases. So pressure will goes. Yeah. So pressure will goes on decreasing and volume will goes on increasing. Right? Now see, all of you. So okay. Now all of you just a minute. Yes, is that okay now? Yes. Okay. Now see, all of you see here. Now see, when I move from point number 1 to point number 2, what happens? Pressure decreases, at the same time volume increases. Right? Now see, when pressure decreases, volume increases, such process it is called as expansion. Okay, when we move from point number 1 to point number 2, what will happen? Pressure decreases, volume increases. Okay, and such process it is called as expansion. Such process it is called as expansion. And during expansion, always work produces. During expansion, always work gets produces. Okay, so see, we will try to finish this one only. So during expansion, the work produces. During expansion, there will be always work produced. Work will be always get produced during expansion. Now the reason why I am plotting this diagram is listen, if you calculate area below this process, I repeat, if you calculate area below this process will give you the value of work done. Okay, I repeat, see, if you need to calculate work done during 1 to 2, you can use this formula. What is that formula? Integration Pdb for process 1 to 2. By using this formula, you can calculate work done. But alternatively, if you need to calculate work done, what we will do? We will plot the process 1 to 2 on the PV diagram. We will plot the process 1 to 2 on a PV diagram, and we will calculate area below the process. We will calculate the area below the process, and area below the process will give you the work done. Thing is, you just need to calculate only the area below the process. It will give you the work done. So work done, you can calculate by two methods. First is by using the formula integration Pdb, and second by calculating the area. How it is? You can see. Formula for work done is Pdb. You can check Pdb. Formula is Pdb. So when you plot any process on a PV diagram, area below that process will give you work done. I repeat, when you plot any process on a PV diagram, area below that process will give you work done. Okay, so that is the reason why when you plot the process on a PV diagram, area below that process will give you work done. The reason is formula for work done is P into dV, integration P into dV, right?
अब यही message
So is that okay? Is that okay to all of you?
Hello.
Is that okay to all of you?
Yes, sir.
Okay, so is it okay?
Yes, sir.
Yes.
Yes, sir.
Is that okay, all of you?
Yeah.
नमाज का टाइम हो रहा है, बाद में कंटिन्यू कर सकते हैं लेक्चर?
Yes.
Yeah. See, yeah. Okay. Now see, all of you. So see, whenever the arrow is going downward, it's the expansion. Okay. But if the arrow is going upward, it's a compression. Both the cases are possible. So whenever expansion, that is arrow is going down, the power gets produced. Whenever there is a compression, okay, the arrow will be in upward direction. Okay, and the power will be get consumed. Okay. So in expansion, arrow is downward. In compression, the arrow is upward. Is that okay? Is that okay or not?
Yes, sir.
Yes, sir.
Okay. So what we'll do? Okay. Today I will conclude the session. Okay. And in the next session, we will continue with the remaining part of this module. Okay. Followed by the derivations and the numericals. See, this is the theoretical part. That is the reason why I'm explaining it on a
Hello, sir.
diagram and. Yes.
Can we see the video afterwards? Means in a Google Classroom.
See, I'll be uploading this video, okay, on the
Yeah.
YouTube, right? The
Sorry,
reason is
YouTube.
that, see, this video those who have missed the lecture, okay, due to certain unavoidable conditions.
So if we didn't understand some points, we can see that. No, that's all.
Yeah, that also. Only see the videos. It should not be. Okay, live interaction. It's most required, right? So what you do, you attend regular lectures, and still if you miss any lectures or if you're not able to get the concept, you can again go through that session, right? Is that okay?
Yeah, yes, sir.
Yes,
Okay.
sir.
So today we will conclude the session, and in the next session we will continue with the remaining part.